All right, so last class we talked about sequences. And so sequences, an infinite sequence that goes on forever, it's just the terms. And I said there's two of them. There's another term that's very similar to it, that sounds similar, and those are series. That's what we're going to talk about tonight. The only difference between a sequence and a series is the summation of that sequence. Okay? So, in general, if you think of, we're just going to add a bunch of numbers together, do you think that's ever going to converge? Good. Give me an example.
No. Like
where you can add an infinite amount of numbers, but it's going to come to one specific number.
Like 1 plus x in that series, it'll eventually go to 1, right?
Well, if you do 1 plus.
Sorry, 1 over x and like plus 1 over.
Oh, like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5.
Go to 1.
You'd be shocked about that one, actually. No. That one's actually.
It's like the 0.
No, that one right there. That series has a very specific name. It's known as the harmonic series, and it's actually one of the series we're going to talk about today, because that's one of the series that you think would converge, because that's what you're thinking. Like, okay, you're adding it. It makes sense that it would converge. It actually doesn't. But we're going to do that one at the end of class tonight. That's actually one of the last ones we're going to look at. Is the harmonic series and how you would actually figure out why it doesn't actually converge. The easiest one to do, actually, the one that most people think of, is if I tell you to walk halfway to the door and continue walking halfway to the door. Will you ever reach the door? No. In reality, yes, because you can't, eventually you're going to bump your head into the door. But if you actually were just taking half steps to the door constantly, you're never going to actually reach the door. However, the distance doesn't get longer. So if you start 10 feet away from the door and you're going halfway the whole time, an infinite number of steps, you're only going to walk 10 feet. So it does converge to an actual value. So that's where you think about convergence. A lot of series don't converge. Actually, the vast majority of series don't converge, because you're going to sit there and add a bunch of numbers up and it's just going to go to infinity, because that's just the way the series would work. But there are quite a few series that do converge, and those are the ones we're going to be starting to look at how we determine if they converge or not. So, but the first one we're going to look at is actually what a series is and how it works. So here is the definition of a series. So there's a few different things on this slide that you want to actually understand. Like it's a little bit. And a lot of it is really notation. So that right there, that's the summation symbol. It's the capital sigma. And the I is your index. So a lot of times that'll just be n equals 1 and the n up top will be infinity. That's what you see up here. So typically it'll be that, written like that, and not with the I equals 1 to n. The reason it's on this one is because this is a partial sum. So that's where you see the s sub n. So if it was s sub 3, it would be just the first 3 terms, be a1 plus a2 plus a3. So that you can do partial sums, where you're looking at just a very specific amount of them. Okay. And we do that to start looking at patterns and seeing if what's happening to them. See, does it actually go to a specific value or not? If, as n goes to infinity, the partial sums does go to an actual number, we call that convergent. So if it actually goes to s, which we use as for sum, so as you go all the way to infinity, if it goes to a specific number, when you add them all up, that would be your S, and that's known as a convergent series. If the sequence goes off to infinity, then that series would be divergent. So these are the terms you're going to hear quite often. And actually, after this point, pretty much everything we're looking at is going to be a series that we're looking at. The sequences comes into play as that's where we're going to be looking for limits and stuff like that and the sequences. But the actual problem is going to be, is this series a convergent or divergent? All right. No problem. Take a minute. You're fine. It's like, no, just, yeah, just, it doesn't have to be perfect. It's like, yeah, most of mine are going to be like that.
Took a really long time to do the infinity. Like I just didn't get my hand there. It's like a lefty thing. Took a long.
Great thing about computers, sometimes I'll just sit there and do that. I'll just make an 8 and then rotate it. But I've gotten pretty good at now, right? My infinities.
I'll try to memorize the old codes for things.
Oh, I have my symbol box in Word that of all my common ones that I use all the time now. We good? Maybe. Yeah, I have the symbol box in Word gives you like 12 symbols. And most of the time when I'm writing, like I don't use more than like 5 or 6 at a time. So all right. So suppose we know that the sum of the first n terms of a series is this. So this is the partial sum. And it's saying that if you add everything up to n, it's going to give you that answer. So it's telling you that S, or that's the partial sum of the series. The question is then what does that go to? So if you have the actual, like the equation for it, so like I can plug in any value and get that point. Since I've got the equation for this, I can actually just do it like I was doing my sequences and do my limit. So in this case, I would look as the limit as n goes to infinity of 2n over 3n plus 5. And we're going to divide everything by n. And this goes to 2/3. Or as I tell my Calc 1 class, if you want to think about your pre-calc brain, the degree on the top and the bottom is 1, so it's the leading coefficients. So the sum of this series is 2/3. Yeah.
So the 2 n's cancel out. That's 2. 3 n's cancel out. That's 3. How does the
Because it'd be 5 over n,
oh,
and that goes to 0. Yeah. Okay. Does that make sense? Okay. Let's look at this one. So we've got 1 over n times n plus 1. So as it's written, there's not much I can do. However, we did learn some methods to break up fractions that might be able to help me. It was one of the methods that we learned how to break up fractions. Think back to chapter 7.
like the A, B?
Yeah. We did partial fractions. So we have 1 over n plus 1. equals a over n plus b over n plus 1. So 1 equals an plus 1 plus bn. So if we plug in 0, we get 1 equals a. So that was n equals 0. And if we plug in -1, we get 1 equals negative b, which means -1 equals b. So this series is 1 over n minus 1 over n plus 1. All right, we good to there so far?
So just put the n equals 1 in there.
Yeah, so partial fractions, remember we're using the ones basically to cancel out a term.
There. Just plug the n equals 1 in.
Well, you're going to plug in n equals 1, n equals 2, n equals 3, n equals 4. So as of right now, I haven't told you another way to do this except for to possibly use partial sums. So that's what we're going to look at and see if we could find a pattern for this one to be able to come up with, does it converge or diverge?
Says it.
Oh, sorry. Yeah, so show it does converge. So it doesn't matter. So we're going to look at this one and we're going to look at some partial fractions for it. So if I plug in 1 for n, what do I get? So I get 1 over 1 minus 1 over 2, right? That's when I plug in 1, correct? Okay. If I plug in 2, what do I get? Okay. If I plug in 4 or 3? I plug in 4. So that's going to continue. And if I plugged in n, I'd get 1 over n minus 1 over n plus 1, right? Okay. If I'm going to combine these, because summation is adding all those terms up, right? All right, so let's look at, what do I got? So I got 1 minus 1/2 plus 1/2, right? So those two should cancel each other out, correct? Okay. And then the 1/3 will do the same thing, right? And the 1/4 would do the same thing. The 1/5 would do the same thing too. There's a 1/5 over there. I just didn't write it out, right? What about the 1 over n?
That'll cancel out.
Yeah, because if I did the one before it, I'd have 1 over n minus 1 minus 1 over n, right? So that one would cancel out with that one. And all that's left in this one is 1 minus 1 over n plus 1. So the sum of this equals 1 minus 1 over n plus 1. Huh? Yep. You did. And now if we look at that as the limit as n goes to infinity, because that's what we're looking at originally, that goes to, this is going to go to 0, so it goes to 1. So this sum, so S equals 1 in this case. Because everything's going to cancel out except for the very first one, and that last term is basically 0. Yes.
Should we expect to use partial fractions often?
No. I'm going to show you a bunch of other methods to be able to do these. Partial fractions works really so partial fractions is one of those ones that always works. It could be a lot tougher for you to figure out like where things go, and you might have to do a lot more of them to figure that out. But partial fractions really helps us like understand what's going on in terms of the sequences before we start looking at, here's the integral method to be able to find it, or here's the alternating series method to be able to find it, those type of things. Okay. So most problems you are not going to have to do out partial fractions or partial fractions and like writing out the partial sums. Okay. Questions with this one? We got it? Okay. All right. So there is a couple really like popular series that come up quite often. The very first one that we're going to look at is known as the geometric series. So you might have remembered from some of your algebra classes, you had an arithmetic sequence and a geometric sequence. So your arithmetic sequences were typically your additions. Your geometric series were the multiplication ones, where you're multiplying something over and over again. So just because we have the sequences, we can have them as series. So a geometric series is a ratio that's raised to the nth power. Okay. So we typically see it written as AR to the N or N minus 1 or N plus 1, depending on where they want to actually start. That up there can vary. We want to get it back to the N minus 1 to be able to do this concept here, but that up there can actually vary. So this is one of those series that all we need to do is find the R, and then we can determine if it converges or diverges, which makes this a very powerful one, because if we can find that R, we know that series is done, and we can use that series to do other stuff. Makes my life a lot easier in some situations. So if the ratio is less than 1, the geometric series will converge. Okay, so basically, if it's a fraction, can't say it's a fraction because we can have fractions that are greater than 1, but the way that most people think about a fraction, if it's a fraction, it's between -1 and 1, it will converge. If the ratio is greater than or equal to 1, it will diverge, which means it will diverge even if it is 1, which kind of makes sense, because if you're adding a 1 a million times, it's going to keep going. It's just going to keep going bigger and bigger. So, but like the one example that we talked about at the beginning with walking halfway to the wall or halfway to the door, that's a geometric series, because it's half, then a quarter, then an eighth, and it's 1/2 to an actual power. And since the ratio in that case is 1/2, it's going to converge eventually. Okay. So if it converges, my sum is that always. Okay, so if my R is less than 1, the absolute value of R is less than 1, it's going to converge, and that is what it's going to converge to. Okay, which is very nice because we can come up with a very specific value to it. I am not proving it. Go ahead.
So that equation is for partial sum?
No, that is the infinite sum. Yes, that is the actual infinite sum. So we don't even have to go through and do all this stuff that we just did here. If I identify it as a geometric series and you know it converges based on that R, that's the answer. We don't have to do the limits and all that other stuff. We just plug in A, plug in R, and we have our answer. Okay, which is actually very powerful because most series you are not going to be able to find what they converge to. You can approximate it, and we're going to look at some methods on how to approximate and get close to it, but you're not going to be able to get an exact value out of it. The geometric series is one of those ones that we can actually find an exact value to. Okay. All right. Let's look at one. So this is a geometric series, but it's not in the correct format. So we have to get it into the correct format. So for a geometric series, remember it's n equals 1 to infinity of a r to the n minus 1. So I need to know a, and I need to know r. A is the starting value, and r is the ratio. So what's my starting value in this case? Or just 5. We don't have 5. What's the ratio? What am I multiplying each term by? So the sign switching, right? So I know I'm multiplying it by a negative. The bottom looks like it's being multiplied by 3, right? So, because if that was a 1, 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. What about the top? 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, so 2. So my ratio is 2/3, or negative 2/3. So my geometric series here will be 5 times negative 2/3 to the n minus 1. When you're writing this series, you want to make sure that it works. So sometimes making like the n minus 1 or starting off at 1, things like that might not work correctly. So you do want to look at that. Sometimes my first number here, the number that they give you might not be the first number because we want to start a little bit off of that and we have to change things up. So once you write this, check it. If n is 1, 1 minus 1 is 0, so that is 1, correct? Negative 2/3 to the 1, 0 power is 1. 1 times 5 is 5. So my first term is correct. As long as your first term is correct, the way that we did it, the rest of them most likely are going to follow. Do check to make sure your signs follow correctly as well. So if we plug in 2 there, we get the negative 1, that would work. So, all right, so we're good there. So what was the summation of this goes to equals, what was the answer? It was a wonderful little fraction. A over 1 minus r. So it's going to be 5 over 1 minus negative 2/3. So I have 5 over 5/3, which equals 3. So this series equals 3. So here is the partial sums of it. So the first sum is 5. It goes 1. So it looks like it's bouncing. But as we're getting farther and farther, it's getting closer and closer to 3. And if we look at this in terms of a graph, that's what the graph looks like. That's the sum. So as you can see, it's bouncing, but it's getting closer and closer to 3 as we go out. So you can do the partial sums. If you did the partial sums out of this one, you'll see where it's actually getting closer and closer to. So, but the geometric series, we don't have to. Yes.
Looking at the table and looking at the graph, or can you safely assume that it's going to 3?
Yeah.
What if it's going to like 3.1 or something? How do you
Well,
know?
that's the thing. That's where next lesson, when I talk about how we do estimations of sums, there's a method there that we actually use to figure out, okay, I want this to be accurate within 1,000th of a decimal place, or 3 decimal places, or 4 decimal places. It's like, how many terms do I need to go out to find that? And we're going to look at that piece to be able to do that. So once you get out to that, we're going to be able to be accurate within a certain number of decimal places. But at that point, even at that point, it's still an estimation. It's not the exact value. The nice thing about the geometric series is we have a formula to come up with the exact value. And if you really want to be interested, I just didn't feel like going through and doing it. It's not horribly long. It is on page 742 of your book. They actually show you the actual proof out of how they actually came up with that. I just don't feel like going through it today. All right. So you're going to see a lot of geometric series. However, the vast majority of your geometric series are not going to be in the nice format. They're not going to be in the nice nx1 to the n of ar to the n minus 1. They're not going to look like that. This is where your algebra skills come into play. We need to start looking at how can we manipulate this to get it to look like that. Okay. So, what are some geometric rules that we could use? Or not geometric rules, exponent rules that we can use. Yes.
Would you have to first make the bases the same?
So if I want to put them together so it's one base, then yes, I'd have to have the bases the same. There's no way I'm making 2 and 3 the same bases though. So we're not going to look to put the 2 and the 3 together to be one number. We want to look at this as some way that we can put it together so that the exponents will go together. So we end up getting that r raised to something. That r could be a fraction, that r can be a multiple number. It doesn't necessarily have to be a single number. So, yes.
You can separate the 3 to the 1 minus n power times. Or sorry, 3 times 3 to the negative n.
Yes. So we could do that. So we're talking about splitting up those. So we could say, I can also do that. That's going to move that out. And then you want to change this to 3 times 3 to the negative n. You want to do that? Okay. Remember, we kind of want n minus 1. But let's keep going with what you're doing.
I'll put the 3 to the negative n.
Okay, so let's get rid of the negative exponent. Okay. So I'm going to change that to 4 just because I don't feel like writing the 2 to the 3rd power there. And then I still have a 3 up here, and now we're going to put the 3 to the n on the bottom. Okay. Now, remember how we were saying we want one exponent? Those are both to the n power now, right? So I can change that to 4/3 to the n. And there's still 3 out the front. Okay. So now the question is how do I get it to be n minus 1? Nothing you've done so far is wrong. Everything you've done so far totally works. But I really need the n minus 1 because otherwise my first term is not going to be correct. Yes.
First out of the series. Index.
I don't want to do that. Problem is, so if you don't have the n minus 1 term, your first term is not a, which will mess up your summation at the end. So by having the n minus 1, my first term, the ratio goes away and the a is my first term. So if I reindex so that it's not n minus 1, it's just an n, I start off at n equals 0, things like that, then the first term is incorrect and we have to do some more calculations to make sure that I get my first term. So it's always easier to make it so that that works. So, all right, so how are we going to get, we need to get n minus 1 somewhere. So anybody have an idea? All right. Let's play with exponents a little bit. What's that? That's 2 to the 3rd. Right? Is it also that? Yes? Okay. So if this is 2 to the n, what's that? Almost. You were off by
2
one
times
very,
2
very
to the
important
n
piece.
minus 1.
2 times 2 to the 3 minus 1.
Right, but what's the 3 now? Is
Oh,
n, right?
you make that n.
You missed the original 2. Hey, look, I have n minus 1 now. So one of the ways that you can do this, if you just have an n and we want an n minus 1, pull one of those out. Okay? It's not something like, in all honesty, if somebody had come up with that, I probably would have asked you where you've seen it before, because it's not something that like would just pop to the top of your head. Right? Because it's not something you normally would do. Your goal is to put things together to get things as simplified as possible, not to pull things apart and make them more complicated, which is in essence what this is doing. But it does give us that n minus 1. Okay? So in this problem up here, I have the 3. I have 4/3. And then I have 4/3 n minus 1. So now can I put those, the 4 and the 3 times 4/3 goes to what? That just goes to 4. So my series is 4 times 4/3 to the n minus 1.
And A is 4.
So A is 4 and R is 4/3. Is this convergent or divergent? Why? Correct. So it is divergent because R equals 4/3. So if this problem was a question on your test, and I did literally ask you, is this series convergent or divergent? Because that's what a lot of the questions on your test is going to be. You would say it's divergent because R is equal to 4/3. I would not just accept divergent. Okay. And the same concept with the last one where we had it was convergent. You would have had to say it's convergent because R is equal to negative 2/3. So no matter which way it is, you have to tell me how you know it's convergent or divergent. Yes.
Does divergent mean that it doesn't go to itself?
Yes, it's going to go to infinity. If you
plug in A and R into the equation, you get a number.
right, but that's only works
Yeah.
if it's convergent. Notice it says is convergent if that, and its sum is this. So yes, you'd get a number, but it won't mean anything. Okay.
So if I'm plugging in numbers for A and R, and I have A over 1 minus R, but if I'm plugging in an R that's greater than 1, I'm already fucked up.
Yes.
Okay.
Yes. You have to determine that it's convergent before you can use that equation.
Okay.
All right. All right. Be honest. How many of you have gotten antibiotics from your doctor and did not take them the entire time out like the doctor said? Pretty much everybody. Rule follower. So a lot of times, so when a doctor is prescribing you a drug, any drug, the amount of the drug that stays in your system is not zero. So when you take the next pill or the next injection or the next whatever, when you take the next one, you have more of the drug in your system than the initial dose that you were given. Okay? Does that make sense? All right. So when the doctor is prescribing you a dose of 200 milligrams, that's not the dose that they want in your system. You might need a dose of 300 milligrams in your system. That's why you're supposed to take it at a specific amount of time, every like 8 hours or 12 hours or whatever else, because all that stuff's calculated to determine to make sure that you have 300 milligrams in your system, because that's what you actually need in your system to fight whatever you're using it for. Okay. This is why if you're on any maintenance drugs for high blood pressure, cholesterol, anything, and you forget to take it, you're going to feel effects because the amount of drug in your system has now dropped below the level that it needs to be at. Even if you take it a few hours later, that can affect where that drop is. All right. So the question is how do we figure that out? So my nursing majors, which don't have to take calculus, well, they always said, why do I need to know this stuff? I pull out a problem like this. Because even in a pre-calc class, you could do this problem. It's a little more complicated due to its pre-calc, but you can do it in pre-calc. So it's like, would the nurse have to figure it out? No. But it does explain the reasoning on why they're very specific on how often you have to take it and when you need to take it, stuff like that. So, all right. So a drug is administered to the patient at the same time every day. So the concentration of the drug is Cn. So that's just like my partial sums. After the injection on the nth day. Before the injection the next day, only 30% of the drug remains in the bloodstream. And the daily dose raises the concentration by 0.2 milligrams per milliliter. So that's the dose that they're basically giving. All right, so how do we find the concentration after the third injection?
Go day by day.
Let's go day by day. All right, so we're going to make the assumption that C0 is 0. So C1 would be what?
0.2.
So it's 0.2 plus whatever the original, the C0 was, which in this case is just, again, 0.2. 30 times 0. Because it's 30% of whatever's in the system the day before, right? All right, C2. Right, so we're going to take 30% of the day before. So I think this comes out to be 0.26. Yes. All right, so C3.
Plus 30% of 0.26.
So I'm going to cheat. 0.278. Does that make sense? Correct. So, but looking at this, do you think it's going to go to a certain value or it's just going to go to infinity?
That's how long you're taking it.
For the end, to the end of your life, does it go to infinity?
Going up.
But does it go to infinity?
It can't. It literally can't go to infinity because you die.
Put infinity. Like
When
calculate.
it's done.
So we need to figure out. So far, what's the only series that I've actually told you and figured out that we've actually been able to do? Yes. So the odds are this is going to be some kind of a geometric series. Because I've only shown you that. No, so it's 30% in your body left over after a day. Most drugs never actually completely leave your system. They'll get down to minuscule amounts, but it'll always be there. This is why they tell you never to take a ton of ibuprofen constantly, because ibuprofen has a tendency to stay in your system for a very long time and drastically impacts your liver. So, all right. So let's see if we can figure out what's happening over time with this one. So we've got this. I'm actually going to take this and put this on another slide. All right, so we've got this. I'm going to rewrite this a little bit. So C2, because C1's actually we'll do C1, is 0.2 plus 0.30 times 0. C2 is 0.2 plus 0.30 times 0.30 0.2 plus 0. because that is that, right? C3, 0.2 plus.
Technically, zero A is zero.
No. No, and that's actually a very important concept of why I can't do that with that. That you don't want your initial value to be 0. So we're going to start off at day 1, not day 0. That's why n is 1 and not n is 0. So we can start seeing how that 0.30 is kind of like building on itself. Yes? So if we kept going, Cn it ends up going to copy this because it's actually written nicely. So if we look at the series, this ends up being Cn. So we have our initial amount, the 0.2, and then we're adding 0.2 times 0.3 raised to a power, depending on how many days it's been since you got that dose. Okay, because the initial day dose on day 1 is a full dose. On day 2, it's 30% less. On day 3, it's 30% less of that 30%. And that's where those powers are starting to come into play. All right.
Say then was 0.2 times 0.3. Not that whole thing.
So my summation, what's A?
0.2.
Okay. What's my R?
2
Just 0.3. That's my R.
converges.
So this is going to converge because R is less than 1. Absolutely. Now we can use our equation.
I guess intuitively that makes sense because the rate at which it increases decreases. So it'll be like the graph it'll start with a higher slope and then the slope will eventually become a straight line.
Yes. So this ends up being 0.2 over 0.7. So it's 2/7. And if you come out with 2/7 as a decimal, and of course they didn't, which is fine. But it's actually going to converge to 2/7. Let's see what 2/7 is as a decimal off the top of my head. It's 0.
2/8.
Yeah. So there's what it actually converges to. So instead of 0.2 milligrams per milliliter in your bloodstream, the doctor's actually prescribing you 0.285 or approximately 2.29 milligrams per milliliter of the drug in your bloodstream, which you'll get to after a certain number of days as it starts to level off to that point. Okay. And if you miss a dose, it would drop and then you'd have to build it back up to that stage. That's why, like, when you miss a dose, yes, you can take the dose the next day, but it's going to take a couple more days before it builds back up to that level.
You know how like
That would be bad.
you know how when you're driving your car and your fuel gauge goes to 0, but
Mhm.
it's not really at 0 because the engineers thought of that.
Yes.
You actually have more gas in there. But doctors, they can't do that, right? They're not allowed to do that. They're not allowed to be like, oh, they're probably gonna not eat all of this, so I'm gonna prescribe them more. They're not allowed to do
They
that.
can't do that.
Yeah, that's why. Okay.
Because if they did that and you actually did follow the directions, you would harm yourself. Correct. So they have to assume you're going to do what you're supposed to do.
So they can't engineer humans into the
No.
because technically they're not allowed to.
Right. Because that could harm you a lot. All right. All right. So you can start to see how this is like some of these things are actually useful. Like it's not just like, and again, the doctor's not sitting in the back doing these calculations. They're all in a book. They have all the stuff's there. Like they know the dosage and stuff like that. They don't, but like, because the pharmacists and the companies and everything else, the creative have already done all this stuff. But that's why it's important for you to take your medication on time. All right. Well, yes, that's same concept, actually. All right. So I want the fraction for this. So the question is this a rational number or irrational? Why? That would make it rational.
I don't know.
Irrational numbers are pi, e, square root of 2. Those are numbers that go on forever and never repeat. A rational number is a number that can be written as a fraction. So if a number repeats, I can write it as a fraction. The question is what's the fraction? So if we look at this problem, can I write this as an infinite sum or an infinite series?
I'm gonna go with yes.
Because otherwise I wouldn't ask it, right? So then the next question would be, how can I write this as an infinite series?
So
Yeah.
you would do 2, 3 plus, and you would have the 0.017, and then you would plug with
Okay, so 2.3 plus, what's the next number? What am I adding to that to get,
0.017.
okay.
Then you would do something.
And then what's the next number going to be that I would add?
Add a 0. 2 zeros.
And then 2 zeros.
2 zeros. So there's some like multiplication stuff we can do.
And then this one's going to be 5 zeros, right? 1, 2, 3.
That's like 1%. Theoretically, right? Of that 0.017.
It's a lot. It's a small number.
Oh yeah. Do that.
All right. So can I write that as a fraction? What? Let's see how many of you actually remember your decimals. How do you read that?
7,000.
All right. So that'd be 17 over 1,000. What's this one?
Add 2 zeros to 1,000.
Over 100,000. Yeah, it's 5.
Wait, why would
I added 2 zeros. 1,000, 100. There's 5 zeros because it's 5 decimal places. And then this one would be 7. Okay. It's funny, depending on the class I ask that question, depends on the answer I get for how do you read that, because a lot of people don't actually remember the fact that it's 17 thousandths. Like it's 0.017, that's it. No. All right. How can I rewrite the denominator so that I don't have an ever increasing number of zeros? So 17 over 1. 10 to the third. And this would be 17 over 10 to the fifth, 17 over 10 to the seventh. The next one would be 17 over 10 to the ninth, and so on and so forth, right? Okay. All right. So I think we've kind of determined already that this 2.3 has got to like somewhere just disappear off the front. We're going to ignore that for a second because that's just not going to make my life very nice. So let's look at this as my geometric series. So
You do 1 plus 2 and
no,
because I need an n minus 1.
right. So okay, so if we look at this, what's my first term is 17 over 10 to the third, right? Okay. What am I multiplying it by to get the next term? So 1 over 10 squared, right? Or 1 over 100. Would that give me every number after that point? Okay. And it's 2.3 plus that. Is that a geometric series? Does it converge?
Yeah.
Because my R is less than 1, it converges. So since that converges, this is going to be 2.3 plus 17 over 10 to the third divided by 1 minus 1 over 10 squared. So 23 over 10, because we wanted it as a ratio, no more decimals. Then this is 17 over 10 to the third times 100 over 99. Yeah, because that'd be 99 over 100. Actually, let me not write 100. Squared. So 23 over 10 plus 17 over 990. Right? Okay. So what's 23 times 99? I know you guys, some people's got calculators sitting out, so like I'm not going to do this one. 23 times 99 plus 17. Yeah, 2294. Yeah, that's okay. They're both even, right? So I can divide by 2. So 1147 over
I don't know.
495.
Why did you?
Why did I what? You got it? Okay. I was just reducing the fraction. If you divide that in your calculator, you'll get 2.31717171717. This works for every single decimal that repeats. Every one of them. No matter how complicated the decimal is, as long as the numbers repeat at some point, you can do this. And you'll get it as a ratio of a rational number. Yes.
I go to my calculator and I go to the fraction.
It gives it to you as that fraction.
That's how it does it.
Basically, yeah. That's literally how the computers do it. So that's actually one of the reasons a lot of our computers have those calculations, because they don't. So the calculator can't do complex calculations, as crazy as it sounds. It has to take those complex calculations and break it down into simpler things that are basically more of like addition and subtraction. So your calculators do summations of series a ton, because it literally breaks it down to a sum of a bunch of numbers. And depending on how many decimal places and stuff they fit on the screen, depends on how far they have to go out to actually get the number to display to you. So, okay. But that's how all those numbers come up to me, and it'll work for every one of them. All right. Our first test. Well, the first thing that we're going to look at is known as the test for divergence. So remember last class when we were doing the limits of the series of the sequences, and those sequences could come up to a number other than 0. And I'm like, this is a very important concept to understand. It's because of this. If you take a sequence, so this is a series right here. That's a series. That's the sequence. Okay, so if you're just looking at the a sub n, that's the sequence. If the sequence, the limit as it goes to n goes to infinity, goes to 0. So if the series is convergent, then that limit goes to 0. Okay. So if the series is convergent, the limit as the sequence goes to infinity has to go to 0. The question is, does that theoretically make sense? So let's think about this. A series is a summation of an infinite sequence, correct? All right. So if I was going to keep adding numbers together over and over and over and over again, if the last number is a 1 in that sequence, and I added it to the sequence, the numbers before that, is my series going to get higher or stay the same? It's going to get higher, which means it didn't converge. Okay? So the only way for that series to converge is that the last number in my sequence is 0. Because if the last number in my sequence isn't 0, my series got bigger, and therefore it didn't converge. Does that make sense? Okay. The converse of that is not true. Right? Very important. If the limit of the sequence goes to 0, that does not mean it is convergent. Okay? The test for divergence states if it doesn't go to 0 or does not exist, then I know the series is divergent. Okay? So if it goes to anything other than 0, it's divergent. I'm done. I don't even have to think about anything else. I know it's divergent. I don't have to try to come up with the sum of it. It's not going to work. Okay? But the opposite is not always true. We will see series that the sequence goes to 0 and it is divergent. Okay. But the test for divergence helps because that's going to eliminate a lot of those things. If I can look at that sequence and I know it's not going to go to 0, I'm done. I don't even have to worry about it. Divergent, done. We move on. Okay. Right. And that's the first test you're going to look at in most situations is, does the sequence go to 0? And if it doesn't, you say divergent based on the test for divergence, and you're done with that question. You can move on to the next one. Okay. Does that make sense? Or
Do
no?
you just cite test for divergence as the
That's the reason. Yep. And somewhere on the thing, you're going to show me that the sequence doesn't go to 0. Like, you have to show me why it doesn't go to 0. All right. Let's look at this one.
that
Yeah, it's an n. It's n equals 1. A little cut off when I made the. So what is the sequence in this? Okay. That's the sequence. So let's look at the limit as n goes to infinity of n squared over 5n squared plus 4. How would I do this limit? Yeah. Yeah, we divide everything by n squared. So I have 1 over 5 plus 4 over n squared, which goes to 1/5. Does not equal 0. Diverges. Test for divergence. That's how you'd show this problem. Yes, the test for divergence is nice. That's why we do that one first. It will not always work with the test for divergence, but that's why that's the first thing we want to look at. All right. Now we're going to get to your statement at the very beginning of class. So 1 over n. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 keeps going, right? What is the limit of that sequence?
Theoretically, 2.
uh,
0.
1 over n. The limit as n goes to infinity of 1 over n goes to what? 0.
But technically, you're still adding.
Right, but no, I asked what is the limit of the sequence? The limit of the sequence is 0. Okay, so we cannot use the test for divergence on this one. All right, the test for divergence fails because it equals 0. You do not know if it's convergent. And this is the reason, this is the problem that is one of those ones that it's like, it looks like it'd be convergent. It looks like it's going to go to 0. It looks at the numbers are getting smaller and smaller. It's like, obviously this is eventually going to go to a number. Huh? Yeah, like 2 or something like that. But it doesn't. All right, because I don't feel like rewriting all this, I'm going to copy and paste this stuff from the book because it's a lot easier. It's just a bunch of writing. And no, I don't expect you to write all this down. I expect you to see it and listen and understand what I'm showing you. All right, so the partial sum of 2 is 1 plus 1/2, correct? Okay. Yeah. Everybody agrees with that. Partial sum, the fourth partial sum is 1 plus 1/2 plus 1/3 plus 1/4, correct? Okay. Is that greater than what they wrote here? 1 plus 1/2 plus 1/4 plus 1/4.
Yeah.
Yes, because 1/4 is less than 1/3, right? Okay, so this equals 3/2, and that equals 2. Correct? So I know that S4 is greater than, it's greater than 2.
So it oscillates.
No, not yet. Not yet. There's no subtraction, so it's not going to go down. I know what you're thinking. All right. So let's look at the 8th partial sum. So the 8th one is 1 plus 1/2 plus 1/3 plus 1/4, so that's 1/5 all the way to 1/8, right? That's going to be greater than this. I took the 1/3, made it 1/4, and I made all these 1/8. So it's S8, the 8th one. This right here is going to be bigger than whatever I get here. So this right here is going to be greater than, what is it, 5/2? Yeah, 5/2. Okay, it's going to be greater than that. Again, don't know how much greater. I just know it's going to be greater than that. All right. Now you know why I didn't want to sit there and write it all down. Sixteenth partial sum. Same concept, right? They go through, they change some of them to the highest one in that, or the lowest one in that area. So this is going to obviously be greater than this, and this goes to 3.
So it's infinite. Okay.
You said it was 3.
Oh, how do you have second thoughts?
So, all right. So let's look at the pattern that's forming. So S2 well, actually, S1 is 1. S2 is 3/2. Or I should say, actually, those equal. The next one's going to be bigger. S4 is greater than 2. S8 is greater than 5/2. S16 is greater than 3. So what's the next partial fraction that you think they would look at?
It would be the 24th. It would be 3.5.
Why is it 32?
They're going up in the partial sums about how.
Yeah, it's as far as a 2. 2, 4, 8, 16, 32. The next one would be 64. What do you think this one's going to be greater than?
3.5.
So 7/2. And then 64 would be greater than 4. So it continues to grow. So if we look at this, if we look at the pattern that's forming, yes.
Is there a way that, so if I were to graph 1/x, right? And then I wanted to find out the area under the curve from 1 to infinity and take that integration, that comes up with a number, doesn't it?
Try it. I didn't say it didn't. I just said try it. Let's try. Actually, Desmos won't do infinity.
Yeah, I don't know how
Um,
to do that.
So hold on, I'll show you. So you have to do it in the graphing calculator. So if we did from 1 to, it won't do infinity, unfortunately, but it can do a really high number. So let's do 1,000. So 1 over x dx. So 1 to 1,000 is 6.907. What's 1 to 10,000? It's now 9. 100,000, 11.5.
Max at 0.
And if you keep adding zeros, eventually it says undefined, but you can see how it's just getting increasingly bigger. And actually, if you do that, it comes up as undefined.
Well, it's gonna get bigger because we talked about area.
I guess it does that.
Well, yes and no. So your area is not always going to get bigger. And that's actually the lesson that we're going to do next Tuesday, is when we look at the integral test.
But it can't be negative.
Area can't be negative, but area can converge.
It can get.
So the actual rectangles will go down to basically 0 as we go to infinity. So you can't actually find area under an infinite or to infinity with an integral, which is what we're going to look at next Tuesday. So my series here is 2 to the n is going to be greater than 1 plus.
You should change.
Oh, I should switch back over. Yeah, probably should do that. This one. N over 2. That gave me all those, and it basically is going to give me till whenever. So while this sequence, the limit is 0.
Times 2. Oh, you put,
2 to the nth power,
yeah, my bad. But,
and it's 1 over n plus. Yeah. Because if it was 2 to the 3rd power, it'd be 1 plus 3 halves, which is 5 over 2. It's okay. So this is one of those series that looks like it should converge. And it was the first series you thought of when you came into class, which is normally the first series everybody thinks of. You think it would converge because it kind of makes sense that it would converge. The problem is that the numbers aren't getting small enough fast enough. Okay, they are getting smaller. They're going to 0, but they're not getting small enough fast enough to prevent it from going to infinity.
So theoretically, if I squared it, it'd be going down a lot quicker.
Yes,
That's what I'm-
which we will also talk about on Tuesday. That's known as the P series, which is another series we're going to look at. Yes, the harmonic series. So the one we just looked at, this one right here, this series is one that you're going to hear quite often. It is the harmonic series. All right. Couple more things.
So how would you say that diverges? Like what would the
Actually, the definition of this one is it's a harmonic series that diverges. Or after in the next class, when I teach you the P series, you can say P equals 1. Yeah, that's the next thing we're going to talk about. Well, we're going to do the integral test, then we're going to do the P series. So, all right. Couple more things. We're almost done. Don't worry. If the series converges, and only if both series are convergent, is this true? I can pull out a constant. If it's the sum of two series that are convergent, I can split them apart. And if it's the difference of two series that are convergent, I can split them apart. Notice multiplication is not there. Division is not there. It is just addition and subtraction. Okay. Last problem. I'll let you finish writing that down. It'll be back. Yeah. My mouse froze. Coming back. Yeah, Ben and Keegan's in there.
Hi,
Okay.
we're still here.
Everybody got it down or need a second still? That also works.
I just wrote them without the infinity symbol and then minus.
That's fine.
Yeah, we all know that.
Yes. All right. Okay. So let's look at these.
They're both convergent.
I don't know.
Well, I mean, we know they are because you want us to use the little rules you just taught.
So, well, we're gonna have to show that though. Because even if they're convergent, you still need to figure out what they converge to.
But yeah, that's, then you split it, right? Trying to do that.
All right, so let's look at this. All right, let's pull out the 3. Does that look familiar?
Yes, sir. That does.
I'm hoping it does.
We just did it.
It was the first problem we did. Okay, so the first problem we did was convergent. What did it converge to? Was it 1, right? Yeah, the first one went to 1, if I remember right. Yeah, because it was 1 plus or minus 1/2, the plus 1/2, it was that problem.
Oh, we did the partial fraction.
Yeah. So this goes to 1, so 3 times 1, so this is going to go to 3 because of the 3 in front. Because it's convergent, I can pull out the 3. If it wasn't convergent, I would write divergent, I'd be done. We couldn't do the rest of this problem. So that's convergent. All right, let's look at the second one and see if that's convergent. All right, so 1 over 2 to the nth power. All right, so it's geometric series. We don't know if it's convergent yet because I don't know what R is. And I don't know what A is. I need to find A and R before I do this problem. So how am I going to change this to find E and R or A and R? Let's do that first. Can I do that? Is that the same thing? Because 1 to the nth power is still 1, right? So if I was to distribute the n through to both of them, that's still going to give me the original problem. Now we're going to do my little trick that I did before. So I pull out the 1/2, and I have the n minus 1. That's important because if you don't, and this is why I said you want the n minus 1, because if you were looking at this here, you'd assume A is 1. A isn't 1, A is 1/2. So that would change your answer. Okay. So I know this is going to go to 1/2 over 1 minus 1/2, which in this case is 1. Because it's A over 1 minus R. So both series are convergent, right? So that means that I can literally find each one of them and just add them together. So this problem right here goes to 3 plus 1, which is 4. But if either of those series were divergent, we're done.
Like that.
I lied. I want you to, and I don't even, we're not going to find the actual answer. I just saw this one and I really like it. Convergent or divergent? Why?
Because sine of 100 equals 0.
No.
Yeah.
Huh? Sure, I can. You can type inside of 100 and calculate and get an answer.
Divergent, because it's over 1.
Why is it over 1?
Because it's. Oh. Okay.
It's convergent.
Why?
Signs in between 1 and negative. So it's always going to be that bound.
Correct.
And it's a geometric series.
That's what I said. I said sine of 100 is 0.
It's not.
Is it 1 or is it negative 1?
I don't know.
I think it's 0.
It's not 0. Put it in your calculator and get the answer. I know it's not 0. But it doesn't matter. I know it's between 1 and negative 1. So as long as it isn't 1 or negative 1, which I know sine of 100 is not, because 100 is not a multiple of 2 pi, or yeah, of 2 pi. So I know it's not negative 1 or 1. Or sorry, sine is not, 100 is not a multiple of pi over 2 or 3 pi over 2, those things. It's not one of those. So it's going to be between negative 1 and 1. It's a geometric series. It's convergent. Because my ratio is between negative 1 and 1. You're done. So, like, I saw the problem. Like, I like this one. Yes.
If you know that is
In this case, it's also A.
Yeah. The way that without changing, you know, the K.
You can, like, so you do enough of these. This one is going to end up being, this is why I didn't have you come up with the actual number because I didn't really care. It's what ends up being like this. It's just that. That's A, that's R. So it ends up being sine of 100 over 1 minus sine of 100. That's what it goes to. But I didn't care. I literally wanted, it's like, I wanted you to recognize that sine was between -1 and 1. So no matter what happened, you knew it was convergent. That's literally why I saw the problem. Like, I like this one. Let's do this one. So far, just to encapsulate what we've done so far, because every lesson I'm going to add more stuff to this. You've learned the test for divergence. If the sequence does not go to 0, it is divergent, you're done. And we've learned the geometric series. As a geometric series, if the ratio is between -1 and 1, it is convergent, and we have an equation to figure out what it goes to. Okay, so those are the two tests that we've learned so far. The geometric series and the test for divergence. Okay, we're going to continue to use those throughout all the rest of the lessons for chapter 11. So, all right. Have a wonderful weekend. Hopefully the Easter Bunny's next to you.
I don't know.
Do you want